Okay, let's start. First, I wanted to write an email, but I was scared of the response of 180 students, or 50 in this case. So the Monday session, we have a holiday next week, yeah? And we have a quiz next week as well. So there's different things we can do. First of all, I don't know what the schedule is of the Monday students. Okay? So the Thursday session, for those that go on Monday, and I will write a separate email, but we first want to get some response from class, is the Thursday session has only like 10-15 students. So that means that a large majority of the students from Monday can actually move to the Thursday session and follow that session and take quiz 3 there at that time. Okay, that's one possibility. So that will cover, I think we have sufficient place, and we will miss about 10 students. Like we only, if all the students from Monday go to Thursday, we have 60 students and we only have 50 computers. So that means there's 10 students left. So what I also can do is tell the Monday students to just show up at another session. And I'm getting the feedback now from the TAs each time how many students show up. But I don't know what the preferred choice is. If you want to go to Thursday, or if you want to go to Wednesday, the AM or PM session, or you want to go to Friday, or alternatively, I also asked to reserve the room on Tuesday, Wednesday, and Thursday from 5 to 7, so that there's another session then. So I don't know what your schedule is. I don't know if you take the lab session on Wednesday, that at the same time you're free when the students on Monday take the session. So if you're a Wednesday student, that you can go to the Monday session. I don't know your schedule, or vice versa, you know? So that's what I'm trying to understand. Does it make sense to move the Monday students to the Thursday session, or most of them? Is that working or not? I get the impression that that's a yes. Alternatively, we set up a complete other session, which is then needs to run probably from 5 to 7, but some students like to go home, some have a job, I don't know, some have a hobby, I don't know what to do. So I propose, I will write an email, and what I propose is that we will just fill the Thursday session with the Monday students then, and then we have about 10 students left. And we will make arrangements for those to go to a Wednesday or a Friday session. I think that's the best solution. Do you guys agree or not? Is that acceptable? Alternatively, we can set up a complete different session from 5 to 7 or from 8 to 10. But again, I don't know your schedule. So okay, so we'll move forward then with the first approach. So just let the Monday students take their quiz on Thursday, but then again we have 10 students left or so, and we need to accommodate them on Wednesday or Friday. So we'll work that out. You will know that by Wednesday, the latest, each and every one of you. That goes to the Monday session. Okay, so this chapter is chapter 11. And chapter 11 is about numerical integration. Okay, unfortunately sometimes my text is cut off because otherwise I have to use a smaller font size, and some people might not be able to read it perfectly, but it will get better at the end. So in the beginning, so why do we cover a chapter like this the same as the previous chapters? Because you might say, yeah, on Friday you always cover the built-in functions, and they do exactly what we talk about on Monday and Wednesday. So why do we need to know all this that we cover on Monday and Wednesday? Because it's already built in. Because it helps you to understand how you actually program, how you write a function. If you go to Google and you Google a MATLAB, you write something and then MATLAB, you will likely, in 8 out of 10 times, you will find a code on the internet that does mostly, in most cases, what you like the code to do. So lots of things have already been programmed by others, okay? But instead of using that, we go over these different things so that you know that you learn how to program, because that's the goal of this course, yeah? That you know what you got in high school, here at university in terms of math, that you know how to implement that in a computer code. And one of these examples is integration. We know what integration is, and we've done that so far always, most likely, analytically. So we have a function, and we derive the antiderivative or the primitive function, and then we can solve the integral between two values. So we're trying to estimate the area under a certain function. So that is numerical integration, or that is integration. And so what is numerical integration is that we no longer actually derive the primitive or the antiderivative, and instead just compute it with numbers, because maybe the function is too difficult to derive a primitive function. In most cases, we cannot derive a primitive function. That's only for relatively simple functions. And then it's easy integration because you can do it analytically. But again, most functions we cannot do that analytically, and we need to do that using numerical integration. Now, we will talk about Newton-cote integration rules. That's the Trapezoidal Rule and Simpsons Rule. Those are just examples, two different methods to do numerical integration. And we'll talk about their composite implementation, where it's the same as, remember previous chapter at polynomials. We had polynomials that went through all the data, or we had polynomials that only fit a part of the data, and we used, that's called piecewise, and we use that piecewise polynomial to predict the value of y at that part of the data that we're interested in, and not use all the other data. Otherwise we get a very high dimensional polynomial. The same with composite integration is that you don't derive an integral directly for the entire function, but you split it up in different parts so that your approximation gets better. Now, and then we have some rules at the end for open and closed intervals. Closed intervals is where you have some x versus y data, where the integral runs exactly from your first x value to your last x value. That's a closed interval. Open intervals is that you're trying to integrate outside those values. So you have certain x values and y values, and now your left side of your integral is smaller than your lowest x value, and the right part of your integral is higher than your highest x value. Those are called open intervals. Now, okay, we'll go over interpolation again. So imagine that we have some data of x versus y, and we went over like function fitting. We can fit the function through the data. We've done all that. We can do interpolation, and this chapter is about numerical integration. So again, we have some x versus y data. Now, what is integration? Is we try to estimate the area under the curve. Okay, and in many cases it's useful to know the area under the curve because it has some meaning. Now, how do we do this? Now, what we've done in high school and probably at university is we can fit the function through the data, x versus y, so we fit the function through the data. Then we have the function script, like y as function of x is like 1/4 times x to the power 3 minus etc. Now then we have that function, and we can derive the primitive of that function, the antiderivative, so that the derivative of the primitive is the original function, 1/4 times x to the power, etc. Now that's a straightforward approach, okay? So that's analytical integration. The second approach is numerical integration, and that's what this chapter is about. So numerical integration we use in case that we cannot use analytical integration, because simply we do not have a function that goes through the data, or we don't have a function script. So we need an alternative approach. We still have some xy data, but we like to derive the integral, but we don't have a function script. Now let's start with a simple example from high school. Imagine that this is our function, fx is x, and we like to get the integral between x is 0 and x is 2. So the area under the curve of the function fx is x between 0 and 2. Now we learned that we need to derive the antiderivative, so that the derivative of the antiderivative is fx is x. Now we know that the primitive of this function is a half x squared, because if you take the derivative of a half x squared, you're going to have back x. Okay, so now I know the primitive function here, over here, which is capital F. Now we can simply fill in the upper and the lower bound of our integral, which is 2 and 0. Now f2 is a half x squared. X squared is 4, and half times 2 squared is half times 4 is 2. And 0, if we fill out 0 in here, we're going to get 0. So we have the upper minus the lower, and that gives us an estimate of 2. So that's the integral of that function between 0 and 2 is 2. This is a very simple example, yeah, so that we all know again what integration is. Now, unfortunately, we don't work with such a simple functions, okay? We're going to use some more complexer functions. So, and I don't know if you still remember, but MATLAB can actually do analytical integration. So let me clear, just in case you'll see. So I copy paste this. The first thing I say here, and don't use this at home because you might not have the symbolic toolbox, but this is just to illustrate, to compare the numerical integral versus the analytical integral that we're going to compute. So in this case we have a function that's called x to the power exponent minus x. And for some of you it might not be obvious how we derive the analytical the integral of this function. Now, so what I did is that I did that in MATLAB. I was lazy. I first defined x to be a symbol rather than a number, and that's a symbolic toolbox, so you don't have to really know this. And then I state on the second line that fx, that is capital F, is now I like to integrate my function x times exponent minus x. And that function int in MATLAB is analytical integration. Now I have a result. So the analytical integral is minus 1 plus x times exponent minus x. Now, obviously, just to state that here, you might not have this toolbox, this might not work, but in any case, the primitive of this function is fx, is this function. Okay, now we can do whatever we like. Let's plot this function. Let's start with plotting this function. So this is how our function looks, x times exponent minus x, and we have our primitive, so we can directly compute, for instance, what the integral is between 0 and 4. We can analytically derive this. Okay, but again, what if we do not have the primitive function? So we will cover different methods for numerical integration. Now, Newton-cote rules, examples are the Trapezoidal Rule and the Simpsons Rule, and then there's a bunch of other rules later on. Now, you can imagine that we like to, as an example, we like to estimate the integral between 0 and 0.1, a small value here, okay? Not from 0 to 4, but we start with a small interval, and that's between 0 and 0.1. It's somewhere over there. And we like to estimate the integral. And we do it numerically, because we now have the primitive, so we can do this immediately, yeah? Now, the ideas of trapezoidal integration rule is that you actually fit a polynomial function through the data, yeah? And we use one with a Lagrange basis. So the definition of this polynomial is like this. So we have two function values, yeah? We have x is 0. We like to approximate between x is 0 and x is 0.1. So we have two x values. Lower bound is x is 0, upper bound x is 0.1. Now we can define a polynomial that fits through this data, and this is with a Lagrange basis. So we have here L1 times F1 plus L2 times F2. That's the definition. Now, the trapezoidal rule is derived from that polynomial. Okay, and the book states that the solution of the trapezoidal integral is a half times the function value at x is 0 in our case, plus the function value at x is 0.1, and that times h. And h is the difference between x2 minus x1. So in this case that is 0.1 minus 0. So that is the trapezoidal rule. The book doesn't really give a derivation, so if you're interested here, how does this work? How did we get to this? Now essentially what we did is we started with deriving the integral of our Lagrange polynomial. Yeah? Now we can write all that out. We can substitute, this means the integral. Okay? So we can substitute for P1 dx, we can substitute this thing on line 70. Okay? So this thing here, We substitute in here. Now, so what we're going to get is line 87, this rule. Now, if we now define for convenience that h is x2 minus x1, so x2 is 0.1, x1 is 0, and we can substitute that in line 87, then what we're going to get this. Okay, because f1 over h is a constant, so we can remove that out of the integral. Okay, and we have an integral of a, essentially part 1 plus part 2 over there, and so that means we have two separate integrals here, yeah? With 2 times h. Now, you can work all that out, yeah? So this thing here is similar than this over here. Now, if we now fill in our values of, because we know how to take the primitive of this, yeah? That's an half x squared minus x2 times x, yeah? And so the same story over here. So now what we can do, we can actually work that out further. So what we're going to get is this, and now we can fill in the actually function values x2 and x, because x over here is the value of our integral that we're trying to estimate. So if we fill in x2 and x1 at the left and right hand side, then what we're going to get something like this, which is, if you work this out, you see here that you have a minus in front. You can move that in here. Now then you're going to get something on line 94. So this is all very relatively basic. Now if we work first on this first term, because we have two terms essentially. We have this part and then we have this part. Now we can work on this first part. This part is similar to, over here, is similar to this. Okay, you can follow that at home, and now we can again define that h is the difference between x2 minus x1, so that's the step size. Okay, also the width of our interval. x2 again is 0.1, x1 is 0. Now if you fill that out, and we also, if you rearrange this, then x2 is equal to h plus x1. Now if you fill that out in the equation we have over here, what we're going to get is something like this, which you can rework to something like this, and you work that out further, and then what you'll see that essentially almost all terms drop out, and what you have left is that the first part of the integral is f, the function value at x is 0, divided by h, and that was x2 minus x1, times and half times h squared. That's the first term of our integral. But we had, over here, we had two different terms in our integral, yeah? We have here a right-hand side here. Okay, so if we work that out, you're going to get the same result. So essentially what you have is that the integral is this. Now if you can again go further, you can simplify this is equal to this, and then what you have left with is this. And this is identical to what the author proposed in his book. So this is the trapezoidal integration rule. So what do you essentially see here? How do we derive, with the trapezoidal rule, we derive the integral? We just have two function values at f1 and f2, yeah? We average them, we add them, we average them, so we divide this by 2. And then we multiply them by h, and that's the difference in x value. So essentially, this is similar to a triangle. If you calculate the area of a triangle, essentially that's what you're doing here. This is the basis, h. Is the difference between x is 0.1 for you guys here, 0 over here. So that is h, yeah, the difference between the two. Then we have two function values here, let's say they're like this. We average them, yeah. So we have two function values and we take the average, and then we assume that that counts for the entire interval, and then we have something like this. So essentially we have a half times f1 plus f2 times h. So it's a simple rule. So you just take the first function value, you add the second one to that, you multiply that with a half, and you take the difference in x values between x2 minus x1. Now it's a very simple solution. Now the question is, does this make sense? Now we can test this, and we can calculate what the integral is between 0 and 0.1. Now let me zoom in a little bit to make it easier. So what we're trying to do is we're trying to estimate essentially what is the area under the curve between these 2 points here. Yeah? So if you can imagine there's a straight line or so, that's essentially what we're doing with the trapezoidal rule. Yeah? So if we take the average of the two, we get over here, and then if we assume that that holds for the entire interval, that's h. H is 0.1, that's x2 minus x1 is 0.1 minus 0, and we multiply that with the average of the interval. Then we get an estimate of the integral. So that's what I'm doing over here, because our function here, oh, that's our new provost. Yeah? You guys know him or not? He is an FBI most wanted reason. No. So here, the integral here is the trapezoidal rule tells us, very simple, is a half times the function value at f1 plus the function value f2 times h. H is x2 minus x1. So our estimate is that the area under the curve is about 0.0045. That's our numerical estimate. Now, obviously, we also have our fx. This is our analytical function or our primitive. So we can derive the actual analytical estimate, and that is 0.47, 0.047, okay? So, and here I just compute fx upper bound x2 minus fx lower bound. So what I did here, I compared the numerical integral with the trapezoidal rule with the analytical integral. And what you see, they're pretty close. Now, fantastic. Okay, that's what we like. But unfortunately, it makes sense that's really close, because in this interval between 0 and 0.1, the function behaves almost linearly. So using that approach where we take the mean and multiply that with 0.1 gives a pretty good estimate, because essentially you're just trying to calculate the area of this triangle somewhat, yeah? Now we know how to do that. It's the half times the basis times the height, and that's what we're doing. Okay, so this is the basis, h, and this is the height. And then we do that times a half, because we don't have the entire square, we only have half of that square, yeah? But we have to add a little bit to that because the function value is not 0, and that's what's done with our trapezoidal rule. Now, that works really well in this case because the interval is really small, but now we apply it to the interval between 0 and 4. Does this rule also apply between 0 and 4? So what's the rule again? A half times the function value at x1, now let's say it's 0, times the function value of or plus the function value at x is 4, now that's about 0.08, so what we're going to get is a half times 0 plus 0.08, and that's 0.04 times h, and that's 4 minus 0, yeah, this is the basis, 4 minus 0, and then essentially it's a triangle, so what we're going to get is 4 times 0.04 is 0.16. We're completely off. The area under this curve is not 0.16, it's much higher. Because if we apply the trapezoidal rule, we just use this point, and then we have this triangle, and we think that the area is just here. But this is the entire area. We missed this entire part. So we're off. And we can show that here. If we do it between, the analytical integral is 0.9 between 4 and 0, whereas our estimate with the trapezoidal rule is 0.1465, what we more or less computed already just a minute ago. So we're completely off. So this is not desirable. So we have a simple rule, but it doesn't apply perfectly. There needs to be improvement. So you see a big difference, okay? And that makes sense because this function is not linear. Maybe it's linear in this domain between x is 0 and 0.1, but certainly not between 0 and 4. We have this curve. So that's why it's not perfect, yeah? So that's why people said, okay, you know what, to solve that problem, we don't compute the integral directly between 0 and 4 by stating that x1 is 0 and x2 is 4, but instead we use smaller intervals. So we essentially apply the trapezoidal rule on small intervals. So we can calculate the area, for instance, according to the trapezoidal rule for this, for that, all these little intervals, and then we add up the total. That gives us the total integral, and that's the composite rule. Okay, the composite trapezoidal integration rule. Essentially the same, but now instead of directly only using two x values, so x2 is 4 and x1 is 0, and then a half times 4 minus 0 times, or times the two function value, times the sum of the two function values. Now what we do, we just divide it in different what they call panels. Okay? So then what we get is line 156. And that's our new rule, where now we have h. H is the difference between two subsequent x values that you use for the panel. So that's the panel width times the half times f1 plus f2 plus f3 all the way to fn minus 2. So n is the number of data points we have. Fn minus 1 plus and half times fn, the last data point. Okay, so that's on page 6 of, that's in equation 11.8 of the book, okay? Now, this is similar to this statement, written more in MATLAB style, where we simply say integral is h times the half times f1 plus the sum of the function values from 2, the second function value, all the way up to the last function value minus 1, and then plus and half times the last function value. And the step size here, we assume here that the step size of all panels is the same. So the step size is calculated by simply taking the last x value minus the first x value divided by n minus 1. Okay, because if we have 10 x values, we have 9 panels. Yeah? If we have 3 x values, x is 0, x is 1, x is 2, we have 2 panels, 0, 1, 1, 2, for instance. So we have always n minus 1 panels. N is also called the number of nodes, but the author works with number of panels, and that's n minus 1. Now, let's consider an example of this composite rule, and we use this as an example, this function, okay? Which is called the error function. And why do we use this example? Because it's nonlinear. Okay? So, what we define here is, I define that I use 5 different x values that are linearly spaced between 0 and 1. Yeah, so with 5 x values I have 4 panels. Now, with 5 x values, I now calculate what the step size is, or the width of the panel. Yeah, so now I have my n was 5, my x values are 0, 0.25, 0.5, 0.75 and 1. Now I can calculate what is my h. Now we already know that should be 0.25 because that's this one minus that one, and they're all equal. So make sure that you use equal panel widths, otherwise that h value is not a constant and it becomes a variable. So you can no longer have a single h value here, but suddenly you have a variable h value. You can do that if you like, but I don't recommend it. Now we evaluate the function. Now what you see that this is the original function, but I do not include this 2 over the square root of pi yet. I just calculate my function value, which is exponents minus x squared, which is the last part there. Okay? Ideally, we compute the analytical integral of this and we solve the problem. But imagine that we cannot compute an analytical, we cannot compute a primitive function, okay? So, we do it numerically. So, now I evaluate the function value at these x values. So these are my x values, these are the corresponding function values, exponent minus x squared. Now I have my x values, I have my f values, so now I can calculate according to that composite rule, that's line 177, I essentially now fill out what the composite rule is. Yeah, so that's what I do here, where that was a half times the first function value plus the sum of all the function value up to the penultimate function value plus a half times the last function value. Okay, so this is relatively easy to remember. So this is the panel width times a half times the first function value plus the sum of all the remaining function values except the last one plus a half times the last function value. And we multiply that again with the panel width, assuming that the panel width is the same. So now we have an estimate, but again I left out that 2 over the square root of pi. That's just a constant, and we know that a constant of an integral is just a constant of the solution of the integral. So now we multiply that part here, and so the actual integral now becomes 0.8384. I just left the 2 of the square root of pi out, and if you want, you can include it here. So if you include it here, 2 over the square root of that square root of pi, then you can remove it from here. Okay? So it doesn't matter, I can put this here, like this, yeah? and I can leave it out then on line 179. You get the same result. But for convenience, I just did it here. It doesn't matter what you do. Now, the exact integral, we compute 0.8384 between 0 and 1. The exact integral is 0.8427. And we don't compute that here analytically. You can do that at home. Okay? So the answer is pretty close. Yeah? So we have a very simple solution now that uses numerical integration with the composite trapezoidal rule, which is essentially this rule. Now the author wrote a function that does this. This is the function that says the integral is, that's the outcome of the function, is equal to the function name. Now that's trapezoid.m. Then fun is the function name. That could be an inline function, for instance. A is the lower bound of my integral, b is the upper bound, and n panel is the number of panels you like to use. Okay? Now, that's what this function does. And n, the number of nodes, the number of x values, is equal to the number of panels plus 1. If we have 5 panels, we must have 6 different x values. Then we calculate what the step size is, or the width of each panel. That's essentially b minus a, upper bound minus lower bound, divided by n minus 1, or divided by the number of panels. Yeah, this is the same. I can remove n minus 1 and replace it with n panel. Then I have h, I have the width of each panel. Then I define here the different x values. Yeah, I have the number of nodes I like to use. I have the width. Then I define, okay, I have my lower bound a, I have my upper bound b, and then I divide this in number of x values, and n different values I'm going to get here. Yeah, equally spaced. Now I evaluate the x values, and then here I fill out the function, the composite rule. So that's essentially what we just did, but now with a function. So we can do the same here. You can see that we're going to get the same result. So again, this is the same function that we just did. I define my lower bound is 0. I want to my integral needs to be between 0 and 1. So a is 0, b is 1. And now I just execute my function script here, trapezoidal, and you see you get the same result, 0.8384 that we just computed. And here I put again 2 over the square root of pi in front. I could have put that in my function script, so then you can remove this and you put this 2 over the square root in front of this exponent. So input is the function, inline function, a 0, b 1, n minus 1. N is the total number of x values, so the number of panels is equal to number of x values minus 1. So this is our analytical estimate, or our numerical estimate, 0.8384. And our true answer was 0.8427. So we're pretty close, but it's certainly not perfect. Now, we used, in the previous case, yeah, what we just discussed, we used 5 different x values. So you can imagine that if you use more x values, so you divide your interval in more x values, that your estimate will get better. Now that's what we can do here. Again, the same this is now a different function going back to original function, and we can evaluate that with 20 different panels. And we're going to get let's see here, we're going to get an estimate of 0.9542 for our function x times exponent minus x. And again, we use the dot in the fun so that we can work with factors, yeah? You should know that by now. So we execute our composite rule after that, and we get 9542, whereas the true estimate is 9084, derived from analytical integration from our function fx. Okay? Now, it's pretty close, but not essential. So the author then wrote a script where he showed here for that function x times exponent minus x, a little script where here we have the number of x values, here we have the width of each panel, here we have the estimate that we get with the trapezoidal rule, and this is the difference with the analytical result. And this is something not so important, okay? So what you see, if you use more x values, that your estimate, your error, the difference between your numerical estimate and the analytical estimate becomes lower, yeah? So you need about maybe 65 different x values to get a reasonable estimate of the analytical integral, because the difference is pretty small with the analytical result which we had, which was I underscore analytical is 9048. I believe this was, oh, there's another function. So anyway, the difference with more x values, I think this is, which function is this? That we, let's see here, which function is this? Oh, trap, demo trap. So here, this is the function that he uses. This is the exact integral. So he uses probably a different, oh yeah, this is x times exponent minus on the interval 0, 5. So we use 0, 4 so far. That's why we got a different value. Okay, so if we execute our function, we got an estimate of 0.9084 originally, because that was on the interval between 0 and 4, and he integrates between 0 and 5. That's the difference. So a is 0, b is 5. So if you make the upper integral larger and larger, then the area should get larger, yeah? Now this is the exact value of the integral, and here he just writes a demo where he loops over the number of NP values, the number of panels, and now yeah, here we compare. If we execute this again, you see the result here. If you essentially, if you use more x values, so the distance between two subsequent x values gets smaller, 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 you execute the trapezoidal rule, that your estimate is getting better, better, and better. But who wants to use 250 x values to resolve this problem? It's not particularly efficient. Yeah? So that's why, after all this work has been published in the literature, they came up with another rule that's more efficient, which is called Simpsons Rule. Okay? So Simpsons Rule does the same thing, slightly different, but gets a better answer. Now, I just quickly like to go over that there's also a composite rule for discrete data. So far, what we discussed so far involved that we can design which x values we like to use. So we have a function, we can plug in any x value to compute a corresponding function value. So we can design any panel we like. But sometimes we don't have a function, we have discrete data of x versus y. Okay? So we don't have a function, so we're stuck with x values that are given to us. We cannot decide which x values we like to use. So that's called discrete data. Now, line 222 has the answer, or the trapezoidal rule for discrete data. So that's the sum of n is the number of data points, n minus 1. So all the way from I is 1 to n minus 1, half times the first function value plus the next function value, etc., times the difference. So essentially, for each panel, you compute the width and you multiply that with the mean of the two function values. That's essentially what you're doing. Okay? And n minus 1 is, we have n data points, so we have n minus 1 panels. Yeah? Okay. Now, there's a demo, whatever, that he wrote, and that's over here. And that gives an example. So imagine that we have a simple function. Our function simply, we'll just clear everything. Oh, x, fun x. We need to define x somewhere. Which function are we? So let's, if you're lost in MATLAB, which I am often, just copy paste everything. Sometimes it's useful to, here. We'll just copy everything. Okay, so, oh, it's completely lost. I don't know which function we're, here. X. This is strange. Anyway, look at this at home. It's not so important, but this is for discrete data. So this is some function. I don't know which function we defined, which function we're going to use. So we can use this function. Here, we use this as a function. There's different functions in the script. Here. So we define these are our x values. Now we have this as our f value. So this is discrete data. Okay, so imagine that we only have this data. This is what I give to you. I give you the x values and the y values. I don't tell you which function this is, okay? So again, you apply the same rule, okay? So you do the trapezoidal integration rule, but you now can have, this is the estimate 8780, okay, which is between 0 and 5, and the original answer was, I think, what the authors came up with, 0.95. So it's reasonable, but it's not certainly not perfect. So what you do here, you apply the trapezoidal rule for each integral, for each interval. So in this case, with discrete data, you don't have a function, so you cannot decide how many intervals you want. The number of intervals is decided, or panels is decided by the data that's been given to you. So now, the trapezoidal rule needs a lot of x values to get a reasonable estimate of the integral, okay? And you don't want that because it's not efficient, computationally efficient. And that's why someone called Simpson came up with an alternative rule. And this is his rule if you only have 3 data points, okay? So what he did is he fitted the polynomial through the data, he derived the analytical expression, the primitive of that, and he came up with this definition on line 253, where we have 3 data points as example, where we have h is the width of the panel. That's still assumed to be the same, so that's a constant. All panels have the same width, and then we do 1/3 times the first function value plus 4/3 times the second function value plus 1/3 times the last function value. So that's just a rule. I'm not going to ask you to derive that rule. It's just a rule that he came up with. Okay? Where this is the panel width. Okay? And this rule applies if we only have 3 data points. But what if you have 5 data points or 9 or 12 or 17, whatever. So we can generalize this to more data points if we write it out this way, where that's h/3 times f1 plus 4 times f2. So you do 4 times the even function values and you do 2 times the odd function values. And that's how you continue all the way till the last one. So you do the first function value plus 4 times the even function values plus 2 times the odd function values. And the last one is simply the last function value. Okay, now we can illustrate this with the same error function that we had previously. That was 1 over the square root of 2 times pi times exponent minus x squared. Okay, so we can illustrate this particular method, and we define that we have 5 function values of x that are linearly spaced between 0 and 1. Now we calculate here what's the panel width, that's the last function value minus the first function value divided by the number of panels, and the number of panels again is the number of data points minus 1, because we had 5 data points. Now we evaluate then the function values, so we have n, we have x now, we have the corresponding f values, and we have the panel width, which is 0.25. And now we fill out that Simpson rule. And I apply here 2 over the square root of pi in front. I could have also included this in my function script over here, okay? So then, if I put this here, I don't have to put it here. I put it here because it's just a constant. So you don't have to consider it in calculation here. Because it's in any case, you could have put this value over here. Doesn't matter. And this is Simpson's rule. Okay, with 5 function values, because I specified there on line 261 that I have 5 function values. So we have the first function value plus 4 times the second one plus 2 times the third plus 4 times the fourth plus the last one, because I have 5 function values. And I multiply that with the panel width divided by 3. So now we can see what Simpson comes up with, and that's 8427. And you see that that's really close. If you calculate the true answer here, that was somewhere up here. That was 0.8427 for the error function that we just evaluate. So we get the perfect result. And in this case, we only use 5 data points. So the Simpson rule, instead of having to use 250 x values to get a reasonable estimate, we just get it with 5. Yeah, it's way more efficient. So you can try this with a different function. So the author wrote a script that's called Simpson, and that does exactly what we just talked about, where he defines that the total number of nodes that you're using is 2 times the number of panels that you define, and the number of panels here is a slightly different meaning as illustrated previously, plus 1. Then he defines based on the number of x values, and he calculates the step size, so the width of each panel. Then he defines the x values, which is the lower bound with step size h up to the upper bound. So then we have n values of x that are equally spaced between a and b. Then we calculate the function values at each x value. With we evaluate that infall function fun, and here is our Simpson rule. And here we go back to what I said earlier, h over 3 with the first function value plus 4 times the sum of the even function values, because it's 4 times an even one plus 2 times an odd one plus 4 times an even. So you specify that you start with the second function value, step size is 2, so that you have only the even ones up to n minus 1. And then you add to that 2 times the sum of the odd function value. So that's a third with step size 2 all the way to n minus 2. And the last function value. So this is Simpson's rule. Okay? So I expect you to know the simplest rules, okay? But again, they're implemented in MATLAB. Now, this is what we just did here. Now with the function that he wrote, we just did it previously, just in the script. This is the same answer, same result, but now we used the function instead of doing this directly in a script here on this screen here. So input to the Simpson function is the function name, lower bound of the integral, upper bound of the integral, and the number of x values minus 1 that you like to use. So what we can show here, I believe there is and now we can also evaluate the same function or different function. Is x times exponent minus x, so this is no longer the arrow function, and we get 9596, whereas the right answer was 9542 if you do it analytically. That's on top of the script. So, and here's a demo, and what you see here is that the exact integral is 95957 something, I believe. And I don't know the exact integrals. What you see here is that the error that you see here between the numerical estimate over here and the true estimate is much smaller at the given number of x values. Remember, with the trapezoidal rule we need like almost 250, and here maybe we only need like 20 or so. We have a pretty good estimate. Okay, so again, this is the number of nodes, this is the step size, the panel width. This is the numerical estimate of the integral for the given function, and this is the difference with the exact result. So this is the advantage of Simpson's rule, is that you don't need, you need far fewer data points of x values, so it's way more efficient. Okay? And that's what computer programmers are always looking for, the most efficient code. Okay? So that's why in lots of literature, still new algorithms are being developed, new methods, so that the computer gets the answer in as efficient as possible, least amount of calculation time. That's the underlying idea. Now, so the Newton-cote rule, this is a general summary. You can read all this at home. And what we end up with is these are the rules. Rule 1 is what we went over today. That's a trapezoidal rule. It's 1/2 times h plus the first function value plus the second function value. Yeah. With h is just the difference in x values, b minus a. Yeah. B was the upper bound, a was the lower bound. So this is essentially computing the area of a triangle, if you think about it. And you can apply this in a composite rule, yeah, where you define this rule for each different panel. You take the sum of all of the panels. The second rule is Simpson's rule. We just went over that. That's 1/3 times h times the first function value plus 4 times all the even function values plus the last function value in case we have 3 function values. And h is now b minus a divided by 2. You have to be careful with that, if you so please study that at home. Then we have another rule, which is Simpson's 3/8 rule, and it's a little bit more complicated, but that's yet another rule to do numerical integration. Then we have another rule, which is the 6-point rule, where we use, this is with 6 data values, and this is the 9-point rule. So you see that it gets more and more complicated, and these rules are just derived by fitting a polynomial function through the data and then deriving these rules afterwards. So what I expect you to know from this lecture, I expect you to know the Trapezoidal Rule and Simpsons Rule for the simplest cases, okay? And of course understand what numerical integration is. Unfortunately, there's not much time to go on tangents because this chapter has a lot of material, so it's quite serious. Also on Wednesday, maybe on Friday we have some time to talk about the barbecue or so. But have fun. This was it for today. And you'll get an email, yeah? And please study these scripts.